Alright, so let's talk about Dijkstra's algorithm. So it's a method for solving the the single source shortest path problem. So you have a weighted graph like this one in this picture. This picture has an undirected graph, which means that these edges don't have direction, but Dijkstra's algorithm works perfectly well in a directed graph as well. And each edge in the graph is labeled with a weight. Okay, so you can think of this as the cost of going from R to B along this edge, right? So it's not the cost of going from R to B, because you could go from R to B also by going first to A and then to B. So notice that that path has cost 5, whereas the supposedly direct route has cost 9. So exactly what we're trying to figure out here is what is the fastest way to get from R to B. And in fact, the single source shortest path problem is to find the shortest path, or the least expensive path from R to every other vertex in the graph. All right, so that's the problem that we're trying to solve. So when we get done, we're going to have something called a shortest path tree. And I think it would be simplest just to explain that when we get to it. I'm going to be using something called Dijkstra's algorithm, which hopefully you're at least a little bit familiar with. You can take a look at the Wikipedia page right now if you're not. And all right, so how does it work? So R here is chosen beforehand to be the source. Okay, so what we're doing is we're finding the least expensive path from R to all the other vertices. So the way we do that is we build this kind of perfect set S. All right, so you can kind of see that in the table here. So initially, S is the empty set. And so the good property that S has is, as we go along in Dijkstra's algorithm, we have this vector D that keeps track of the distance estimates from R to all the other vertices. So you can see what these infinity symbols mean is that initially, before the algorithm even begins, our estimate for how far it is to get from R to A is infinity. So you want that to come down, right? These dA values are always going to be overestimates. And once a vertex gets put in S, however, the algorithm guarantees that the distance estimate is actually the true shortest distance from R to that vertex. All right, so it's not shown here, but the distance estimate for the root R is set initially to be 0, and so all the vertices are put into a min heap, right, or a priority queue, and they're keyed by this. And so what we're doing is in this min heap keyed by the distance estimates, we're popping off the head during each iteration. And so initially we're going to pop off R, because that is the only vertex that doesn't have distance estimate infinity. It has distance estimate 0. Okay, so we're going to do that at each iteration. Okay, so maybe we should just start. Okay, so look through the pseudocode. We're at iteration 1 here now. So what we've done is we've just popped R off the priority queue because it has lowest distance estimate. And now it's in S, right? Okay, so its distance estimate is correctly 0. It's 0 distance to get from R to R. And now what we want to do is we want to relax, quote unquote, all the edges that emanate from R, or all the edges that are incident to R, to use the right terminology. So, all right, so let's first relax this edge that connects R and A. So what does that mean? That means you take R and you have its distance, which is 0, right? And you see if the distance estimate for R plus the cost of going directly from R to A is less than the distance estimate for A. So you can see it's infinity, very easy to beat, right? So using this rule for relaxing the edge, the new distance estimate for A should be 0 plus 3 is 3. Okay, so the edge actually was relaxed because I changed this value, and when that happens I set the parent of A to be the vertex that reduced its distance estimate. So that was R. Okay, so what these things are going to do is these D's are keeping track of the distance estimate, and these P's are remembering the vertices that are the predecessors of these given things on the shortest path tree that we're building. So what's going to happen is when we build the shortest path tree, the predecessor of A is going to be R. Okay. So all these other things are null. So maybe I'll just leave the things blank that don't change instead of boring you with writing. So what else should we do? Well, we only relaxed one of R's edges. Right, I'll put a little X here just to show that it's relaxed. You only have to relax each edge once. So now let's check this edge that connects R to B. It has weight 9. Okay, 9 is less than infinity. So I write 9 here. That means that the parent of B is R. Okay, all right, great. Now this edge is relaxed. And that's it. So what you have to imagine is that these things are floating around. The things not in S are still on, right? So maybe you should think of, where is the priority queue or the min heap or whatever, still has all these other things in it. So it still contains A, B, C, D, E. So what we do is we pop the one off that has the lowest distance estimate. So which one is that? That's A, right? 3 is less than 9 and certainly less than infinity. So we take A here and we pop it off and add it to S. So now it's off the min heap or the priority queue and it's in S. And what we do is we relax each of its edges. So don't worry about this already relaxed edge. Let's consider these. Okay, so is the distance estimate for A plus 1 less than infinity? Yes. So that means the new distance estimate for C should be 3 plus 1 is 4. And that makes the parent of C A. Okay, and now this edge is relaxed. Now let's do this one, right? Okay, so its distance estimate is infinity, so we should replace it with 3 plus 7 is 10. So now the distance estimate for D is 10, and the parent of D is A. And this edge is relaxed. Let's do it here. Okay, so B, now this is a question, right? So now is it true that 3 plus 2 is less than the distance estimate for B, which as you can see is 9? So it is. So 3 plus 2 is 5, which is less than 9, so I relax this edge. Okay, and that makes the parent of B, it was R, now it is A. Okay, so A has lots of things that are its descendants now. Okay, and so this just stays the same, and this just stays the same, and we've just relaxed this edge. So we're done with A, and now we want to pop the lightest thing off the heap. So which one of these, which is not already in S, has the least weight? Well, 3 is the smallest number, but A, remember, is in S. So I have to keep looking, and that brings me over to 4 here, so we should pop off C. Okay, so now C has been popped out of the priority queue, and it's in S, which means that the distance estimate 4 is now permanent. It's perfect. Now let's go through and relax all these edges. So there's only one to check, this one. So is it true that the estimate for C, which is 4, plus 3, is less than the estimate for D? So that's saying 4 plus 3 is 7. Is it true that that's less than 10? Yes. Okay, that makes the parent of D C. Great, and now this is done. Okay, and that's all there was to do. All these other things stay the same. And okay, so we go on to the next iteration. Now these are the things that are left in the priority queue here, B, D, and E. So which one has the smallest distance estimate? So it looks like B, right? B has a distance estimate of 5, which is the smallest. So take it out of the queue, put it in perfect world, S. Okay, so we found its true distance, which is evidently 5. And let's relax all of its edges. So where is it? Okay, so we relax this edge, and we finally get a non-infinite distance estimate for E, because now we have, right, for B it's 5 plus 4 is 9. So now we have a distance estimate of 9 for E. And so its predecessor is B. Okay. I was just kind of worrying that I forgot for C here to change a parent. Did I forget? No, I don't think so. Okay, so we're good. Alright, and so what else can we relax? Can try to relax this one. So is it true that 5 plus 6 is less than 10? Or 7, actually. No, it's not. Okay, so forget about that. And we still relaxed it, it's just that no action took place. So we're done with B, and now everything else stays the same. So this is still 3, 5, 4, 7. And all these things are the same. So R, A, C, B. Okay, great. So now we have D and E, and we have to decide which one of these we want to pop off the priority queue. So which one has the lowest distance estimate? D has distance estimate 7, E has distance estimate 9. This is less. So we pop off D. Now D is out of the queue and into S. And we go through and relax all of its edges. So there's only one edge to check, this one that connects D and E. Alright, so is it true that the distance estimate for D, which is 7 plus 1, is less than this? Yes. 7 plus 1 is 8, which is less. So now the parent of E should be set to D. Okay, and now this edge is relaxed. And that's it. Okay, so now that's good. And for the last iteration, pretty clear that we have to take old E off the priority queue, right, and put it in S. And all of its edges have already been relaxed, so there's nothing really to check here. But we can copy all this information down so that we have the final picture. So now what I'm writing are the results. We know that the shortest distance from R to A is 3, the shortest distance from R to B is 5, the shortest distance from R to C is 4, and so forth. So the shortest distance from R to E is 8, which is not obvious. And we also have the predecessors here, okay? So let me copy those down as well. So what do these tell us? These let us create, if we want, the tree. So I'll go ahead and do that. So I'll color the tree edges blue. So how does it give us the tree? So these actually give us the shortest path back to the root. So let me just do it for E, since that's the furthest one away. This is telling me that the predecessor of E is D. Okay, so that means this edge is in the minimum, in the shortest path tree. Okay, and so what do I do from D? Well, I can look up D here, and it says that the parent of D is C. So go from D to C. Alright, now what's the parent of C? The parent of C is A. Whoops. Okay, so the parent of C is A. And what's the parent of A? The parent of A is R. Okay, so most nodes are in the tree, right? And so notice that the subpath of a shortest path is a shortest path. So this is, if I were to start at C, I would just get exactly what I've gotten so far. If there were a faster way to get to C, I would have done that in the first place, right? That would actually be the shortest path to E. So now the only thing left for drawing the shortest path tree is to figure out which edge to add for B. I can just look it up. So the parent of B should be A. And what I have now is, in blue, the shortest path tree with root R. And so for any node on the graph, for any vertex on the graph, the shortest path from that vertex to R is just following the blue lines. And that's pretty much all there is to know about Dijkstra's algorithm.